talk about the series RL AC lab project, and the basis of this project is just current going through a coil, an inductor. Okay, let's look at that circuit, and a couple of reminders that definitely put the light bulb in here. That is a safety device, so that if you get a short on this side of the transformer, it doesn't create a short circuit that will burn up the supply circuit or the transformer. Just if you get a dead short across the secondary windings, the light will come on. Somebody told me the other day that they were doing this project and they were disappointed the light didn't come on. They thought something was not working. No, that's just an indicator that you don't have a short circuit. If you're drawing a lot of load on the secondary of the transformer, the light might start to come on dimly. A dimly lit bulb is okay. A brightly lit bulb is not okay. Okay, if you get the bulb completely lit, you've done something wrong. Now I want to point out also that this is the relay coil over here on this end. And that's what we're measuring, not the transformer itself, okay? So what measurements can we take on this relay coil with our meters? If it's not energized, we can certainly measure the DC resistance across the coil. That is our R in our triangle, right? We could also measure the current. Once we have done that, we can energize it. Now, let's assume that our transformer is kicking it down to 12 volts or 24 volts or something like that. So you're only going to have 24 volts coming to the coil. So if it's a plunger that you're working with, that a relay coil that is pulling in a plunger, you're not going to pull in the plunger. So don't worry about that. We don't want to pull in the plunger, okay? We just want to energize the coil and see what the X sub L, the inductive reactance is, and the resistance and the current and things like that. So what we're going to measure first, we're going to find the DC resistance. Then we're going to hook it up with this circuit, and we're going to supply our relay coil with, let's say, I've picked one of the transformers that has 24 volts instead of 12 volts. So then I'm also going to measure the current. Now I could break into the current, I could break into the circuit between this point and this point, and that would tell me the current, right? Or I could use a clamp-on ammeter, but remember, a clamp-on ammeter is not very accurate down in parts of an amp. When you get down to splitting an ohm or an amp, you know, clamp-on devices are not very terribly accurate at parts of a reading. So we're going to start out by putting our triangle here. And you know what? I think I need to make this smaller. There we go. We're going to put our PEIZ on our left. We're going to put our trig functions on the right, or triangle functions on the right, and we're going to label our triangle for what we have. What information do we have? And we, just by measuring it, we can get some things like our DC resistance. And we're going to say that we measured 45 ohms of real DC resistance on this relay coil. So we plug that in. And we know by measuring that we have 24 volts. And also by measuring, we measured the current, and it's 400 milliamps, which is 0.4 amps. Okay? So those are three things we can measure directly, and you're going to do that in the lab on this project. And you're going to put those things in your lab report. Okay? Now, to find our impedance, we just divide our voltage by our current, right? So that means that my current is actually, my impedance is actually 60 ohms, because I divide my 24 volts by my 0.4 amps, and I get 60 ohms is my total impedance. So now I'm going to plug that in up here, because that's my hypotenuse, right? Everybody sees that? Z is my hypotenuse, and I've got R is my resistance. I have two sides of my triangle. I can now find the angle and the power factor, and I can eventually find the X sub L. So we're going to do that. And first we're going to find the phase angle. And since we have the cosine, we want to look at that and say, okay, well, the cosine of this angle is what? It's 45 divided by 60. And it's literally, if you take that number, 45 divided by 60, and hit enter, that's the cosine of that angle. Remember, it's just a fractional relationship. It's not that complex. Okay, so we find, whoops, I think I jumped ahead a little too much. So we can find our cosine. Well, maybe not. I think I was thinking of finding something else before I found the angle. No, we found the angle that was, it's 41.4096 degrees. And since we found the angle, we can now find the opposite side, the x sub L, by using the sine of this to find the x sub L, because the x sub L is the side opposite. Okay? Now, if we take the sine of this angle, we'd find that it's 41.4096. I think that's not correct, that's degrees. I think that's the sine. Let me see here. Okay. No, it was 41 degrees. So our angle is 41.4096 degrees. And originally we found that by doing, let's go back to the beginning a little bit. Let me go back up here a little. We found our, that's not the right slide, I don't think. The first 5. Why does it keep going back down? Fighting with the slideshow. Great. Damn. No, it has nothing to do with that. Okay, so somewhere along here we found our angle, and we found that since we had the impedance and we had the resistance, we had the cosine. Did I skip over that? No, here it is. I just skipped the slide, sorry. Okay, so we found that if we knew the cosine, knew that the cosine of the angle is A, which is 45 over H, which is 60, we could use our calculator and say cosine of the angle is 45 over 60, so we can now enter second function cosine. Tell me what angle has this cosine, and then put in 45 divided by 60, hit enter, and that tells us the cosine. It tells us the angle that has that cosine, which is 41 degrees or something like that. 41.4096 degrees. Okay, so I skipped that slide, sorry. Okay, so we found the angle. Then we're going to find the side opposite, and we're going to use the sine to do that. So we know that we have the sine because we have the angle. So if we just take the sine of that angle, and we could just put in sine, second function answer, to plug in the angle that we just found, and that'll give us the sine of this, and that is, the sine of this thing is 0.6614, and on and on. And that's equal to O over H. We don't want O over H, we want O. So if we multiply H times both sides, which is the hypotenuse, so 60 times the cosine of this angle, the sine of this angle, will give us the side opposite. And we found that that's 39.68 ohms of inductive reactance, right? Now, inductive reactance is a fixed thing. Would you agree to that? It's like having resistance, right? Is that going to change? If we add resistance to the circuit, is that going to change? It's not going to change. Okay, so let's go on, and you'll see why that's kind of important. So since we want to know the power factor of the circuit, we just take the cosine of the angle, which is whatever, 41 degrees. Cosine of 41 degrees comes out to be just about 75%. And that's our power factor. That means it's turning 75% of the incoming apparent power into true power. 75% is not what I would call very terribly efficient, right? Now let's look at what happens if we just take the next step in the lab project, and we're going to add a resistor in series going to the coil. Okay? How will it change our triangle? That's our real question. So now our resistance is 55 ohms instead of 45. And our side opposite, is it the same? It's going to be the same, right? It's going to be the exact same, 39.68 ohms. So we have two sides. We have a tangent, don't we? Here we have a tangent because we have the side opposite and we have the side adjacent. So now we have a new triangle, right? And we want to know what angle that thing has. So if we go second function tangent and then 39.68 divided by 55, which is that tangent, that'll tell us that the phase angle is 35.8 degrees. What was it before? 41 degrees, over 41 degrees. So it's come down in angle a little bit. And the lower that angle is, the higher the power factor. And that is the point of this whole project. Okay? Our new phase angle is this blue one in the background. Our old one, 75% power factor, is the original triangle with just the relay. Here we added a resistor, and resistors are creating pure power, right? So it's adding true power to the circuit and nothing else. So it changes our phase angle. Our phase angle became I don't remember, 35.8 degrees. And our power factor, the cosine of that angle, 35.8, is 0.8109 or 81.09%. Now, if you've got something that's, let's say you have a car and it's turning 75% of the gasoline into power to go down the road. Won't you be a lot happier if it's making 81% power out of that gasoline, turning 81% of it into movement? Everybody's going to be a lot happier at higher efficiencies. Okay, let me pause this a second. I'm going to go ahead and stop this, and you guys can look at it again at your leisure.